My dear people, welcome to the last section of this particular lecture on buoyancy and hydrostatics. This is Dr. Venkat. I remember when I was 5 or 6 years old, I made a paper boat. That was my first paper boat. Yeah, and I let it to float in the water. It really floated, and I was so very happy. Yeah, and I remember like a few years later when I made a paper boat and I had the same size paper, one more sheet of paper. I just made it into a paper ball and then I threw it in the water. The paper ball actually sunk, whereas the paper boat floated. I really wondered what is the reason that the paper boat floated whereas the ball sunk. Oh, that was really interesting. And only after a few years later, I was able to understand why, thanks to the buoyancy principle, which we are going to be discussing now. Well, let's get going. hmm, Talking about paper boats, shall we? Huh? Well, I remember an incident. Two of my very good friends, Peter and Carolina from Warsaw, we studied at the university together in Plymouth. We all decided that we'll go to the Dead Sea together. A year or so ago, I had a call from them saying, "Oh, Venkat, we are in the flight. Guess where we are going?" I was like, "Where?" "We are going to Israel and then we'll send you some photographs from Dead Sea." I was like, "Oh, yeah, thanks, guys. Cheers. Cheers for that. Cheers for making me jealous." And then 2 days later, they sent me photograph floating in the Dead Sea. I was like, "Oh, yeah, that makes me feel so wonderful, guys. Thanks." Yeah. But my question to you guys is this. Why were Peter and Carolina able to float in the Dead Sea, whereas when I tried the same thing in a local swimming pool, I couldn't float, I just sank? What was going on, my dear people? Yeah. So in the Dead Sea there was some force. Yeah, there was some force that acted on them, that made them to float, whereas in the local swimming pool there was that particular force, but it was not sufficient to keep me afloat. What is that particular force all about, my dear people? Let's have a look at it, shall we? Okay. I do not want to be discussing about how Archimedes identified his principle. This is the guy, a representation of Archimedes. And he screamed Eureka running naked in the street, etc. No, you can look at it online. What does Archimedes' principle say? Anything that floats in water or any liquid, anything that sinks, etc., can be easily identified. What is the force that is acting on the body? All those things by Archimedes' principle. As Archimedes' principle comments, the upward buoyant force. So if there is a body that is submerged in water, it is experiencing an upward force, and that force is called the buoyant force, FB. Yeah, exerted on a body that is immersed in a fluid, whether partially or fully submerged, is equal to the weight of the fluid that the body displaces. I see. Okay. So the buoyancy force equals the weight of the fluid the body displaces. Fantastic. Okay. So if the weight of the water displaced is less than the weight of the object, then the object will sink. Okay, that's fine. Yeah, because the weight of the what I said, the weight of the water displaced is the buoyancy force. So if the weight of the body, yeah, this is the weight of the body. So if the buoyant force is greater than the weight of the body, then the body will rise up and it will float. Whereas if the buoyancy force is less than the weight of body, then the body will sink. This is what Archimedes principle is all about. It is really simple, is it not? Yeah, as long as you get your head around it, it's quite a simple one. So this is what I want you to remember. Yeah, the more the water that is displayed, not displayed, displaced. I think I'm a bit sleepy. So people, the more the water that is displaced, the more buoyancy force. Yes, and the less the water that is displaced, the less the buoyant force. Yeah, this is what I want you to remember. If more water is displaced, it means that the weight of the displaced water would be heavier, would be more, so the buoyancy force would be more. Yeah, fantastic. If you are not sure about it, my dear people, pause the video, go look at Archimedes principle in the booklet that I have uploaded by Rachel, and also also in the books, in the reference material, or just read this, whatever is written. Is that okay? So why does a body float or sink? Yeah, so do you remember I told you the pressure equation P equals rho g h Pascal? Yes. So when this body is submerged in water, the top portion is going to experience a pressure of rho gh. Yeah, that is what I have indicated here. Rho gh is the pressure that it experiences. Yeah, if you think of it, my dear people, as the height, otherwise as the depth increases, the pressure also increases. So look at this particular point, the end of it. Here it should experience more pressure. Yes or no? Because the depth, this depth is 1 meter assumingly, whereas this depth is 2 meter. So the pressure experienced by this surface is larger. That's why I have drawn longer lines to represent the higher pressure. Yeah, also the pressure on the sides would be increasing. Yes, but then since the pressure are equal on both the sides 1 and side 2, the pressure are equal, they'll just balance out. Yeah, whereas here if you think of it, the pressure in the top, the pressure in the top is less than the pressure in the bottom. Yeah, and this high pressure in the bottom, what will it do? It will try to push the body up, and this, my dear people, this pushing of the this higher pressure that pushes the body upwards is nothing but the buoyancy force. This is what creates the buoyancy force, my dear people. Yeah, if you go into a swimming pool, yeah, it's so very easy to lift, uh, what is it, it's so very easy to lift some heavy object when it's inside water than when it is outside water. Yeah, mm, you can easily, what is it, well, I'm sure if you just go into swimming pool or anything, you feel lighter. The reason we feel lighter is because of the buoyancy force that is pushing the person upwards. So if there is a person here, now if there is a person, yeah, in the water, the person is being pushed upwards, yeah, by the buoyancy force. Okay, so what is the formula, my dear people, for buoyancy force? This is the formula. Fb is the buoyancy force equals density times gravity times the volume of the fluid displaced. Yeah, volume of the fluid displaced. In this case, yeah, in this case, the volume of the fluid displaced would be the volume of the body. Yes, in this case, because it's completely submerged, so which means the volume of the body equals volume of water displaced. Is that okay? Okay, now let me put it very simply to you guys. Yeah, look here. If the force of the body, otherwise the force of the body or force of object, or let us call it weight. Okay, if the weight of the object, yeah, is is less than the buoyant force, if the weight of the object is less than the buoyant force, the body will float. Yeah, because the buoyant force is higher, so it will float. Whereas if the weight of the body is, yeah, if the weight of the body is greater, weight of the body is greater than the buoyant force. And what is buoyant force, my dear people? Buoyant force is nothing but the, well, buoyant force is equal to what? Buoyant force is equal to the weight of the water displaced by the object. Fantastic, fantastic. Yeah, if the weight is greater than the buoyant force, then the object will sink. Yeah. Now think of it. What is the weight of the body? Weight is nothing but mg. Yes. And what is the buoyant force? Bf equals, or fb, yeah, fb equals rho g v. Yeah, so mg equals rho gv. This is case 1. In case 2, I've got mg is greater than rho gv, and case 3, mg is less than rho gv. My question to you all is this, my dear people. Yeah, what will happen to a body in case 1, case 2, case 3? Can you let me know? Okay, Archimedes principle can be explained with this very simple picture here. Yeah, it's a very standard one that that is used. So let us take this block that is 5 kilogram. That is what is indicated in the scale as well. 5 kilogram. Yeah, that is the total mass. And then what I do is I just immerse it. I just put it in a beaker of water that has got a spout. Otherwise, water is filled exactly to the brim. And if I put it in, what will happen, my dear people? Water will start to flow into this particular container. Yeah, so as soon as I dip it in water completely, when I look at the scale, it had shifted from 5 to 3. What happened to the 2 kilogram, people? Huh? Exactly, you're correct. That 2 kilogram is taken away by the buoyant force, the upward force that is pushing it. Yeah, so this, so now what is the so I'm really excited. Yeah, so what is this 3 kilograms called as? This 3 kilogram weight, now when it is in water, is called as the apparent weight. Apparent weight of the body. Yeah, so if I write it clearly, the total weight, otherwise weight of the body, yeah, minus the apparent weight equals the buoyancy force. Yeah, okay, now my question was, okay, fluid has flown out of it, water has just dropped into this particular bowl. What I do is I take this water and I weigh it. Guess what? 2 kilogram. It is true. is it not? Yeah. So what does it mean, huh? My dear people? The buoyancy force that is experienced here, it says 2 kilogram, is exactly equal to the weight of the fluid or liquid that is displaced. Well done. Again and again, we are coming to the same point. Do you see? Yeah. Fantastic, fantastic. Now there is one more thing I want you to see from this one. Yeah, in this particular image, let me just rub this all off. In this particular image, there are three forces that are acting. Number one, the weight of the body, and then number two, the buoyancy force, and also there is tension in this particular string, is it not? So there are all these three forces taken together would be the weight equals tension plus FB. Do you see the buoyancy force? That's all. This is quite an important thing for you all to remember. It's just force equation, is it not? Yeah. Fantastic, fantastic. So, my dear people, this is just more of what is it called as more of a revision or some sort of a question for you. Let us say this ball is a football that is placed in a tank of water. Yeah. What do you think will happen to this ball? Will it go up or down? A football, what do you think? Hmm? Go up. Okay, let us say the diameter is 10 centimeter. Yeah, okay, it will go up. Okay, that's fine. Now I take the same diameter 10 of a steel ball. So if you think of it, my dear people, both these balls displace the same volume of water. Volume of water displaced by 1 equals volume of water displaced by 2. Yeah, this is case 1 and case 2. Both the balls displace the same volume of water, but still the steel ball would sink, whereas the football floats. What is happening? What is happening here? Yeah. What is it? What do you think it is? What do you think? Huh? Okay, you want to tell me in the lectorial? Okay, fine, fine. So, people, one way I know that we can make this solid ball to float, okay, is this. So, I take this solid ball, the steel ball, yeah, of 10 centimeter diameter, yeah, I take it and then I beat it into a shape like this, or I beat it into a shape like this, or I beat it into a shape like this, or any shape, yeah, or I beat it into a shape like a sheet, yeah, I beat it into a shape, otherwise I just make it longer and stretch it, etc., and then I put it in water. What, what, what? It is floating. Why? It's the same ball. If this is, let us say, 1 kilogram, this is also going to be 1 kilogram, is it not? Huh? The mass is exactly the same, but why is this floating, my dear people? Yeah. What is it? Exactly. You're correct. As Archimedes says, FB, otherwise the buoyant force, equals to the weight of the water displaced. So, the more the water that is being displaced, because this displaces much more water compared to this, yeah, the more the water displaced, yeah, the more the buoyant force. This comparatively compared to this structure here, this displaces less water, which means the buoyancy force is less. Yeah, again, that is what I'm saying. The more water is displaced, the more buoyant force that there is. Yeah. Hope you are all understanding this concept. Yeah. Again, just to reiterate, the ducks, duckling over here, and also the ship, they float because they displace much more water. I was always under the impression that ships had like a flat base, but no, ships have a base that's quite long like this. They have it for making sure that the water that they displace is much more. Yeah. Okay, now my dear people, how much something sinks? Yeah, how much something sinks? Look at this particular iceberg here. Yeah, let us say the total height of the iceberg is h. Yeah, and the height that it has sunk to is x. Yeah, and the density of ice is rho object, or let's say rho, yeah, let's call it rho object. Okay, and the density of water is rho water. Yeah, so how to find how much of this ice is going to sink? Yeah, so how to find it out? It's a very simple formula, my dear people. The formula is also given in the worked examples, and also there is this there in the booklet. Don't want to repeat it. So the formula, the sinking length x equals the density of the object divided by the density of the fluid in which it is sunk. Here it is water times the total height. That's it. The amount it is going to sink is nothing but the ratio of the density of the object divided by the density of water. Aha. What is the density of an object or any fluid compared with the density of water? What do you think it is? Density of water is 1000, yeah? So density of object by 1000. What is this? Do you remember? Yeah, what is it? Exactly, this is the relative density, or it is also called as specific gravity. Yeah, so it is nothing but specific gravity or relative density times the total height. That is how much it is going to float. Yeah, and also sink. Let us make a very simple calculation, shall we? Wait. Come on, go away, be quick. Okay, let us give it some values. Okay, okay. So let us say that the density of ice, I know. Sorry, guys. Why is it not staying? I have no idea. Yeah. Well, but then I have solved a problem for you guys in the example problems. Yeah. Have a look at that. What do you think is the mass and density of of this particular block? Yeah, this particular block has a total height of 2 meter. It is sunk to a depth of 1.5 meter. This is 1.5 meter. It's not staying. Again, I have solved this problem for you guys. You can easily find out what is the mass and the density of the block just by knowing the total length that it has sunk to. Yeah, and also I have we can easily find out what is Pingu's weight. I just watched Pingu a few days ago. I really loved it. By just knowing how much the block will sink. Yeah, because Pingu is on the top of it. Yeah, it sinks by 5 centimeters, so we can easily find out what is Pingu's weight. Again, I have solved an example problem for you guys. Yeah, I have solved other numerous example problems for you guys as video and also in the tutorial. Have a look at these questions. Try to watch these questions and do it on your own, and then we'll be discussing it in the tutorial as well. Is that okay, my dear people? Yeah, again, these are all the examples that I have done for you guys. Well, anyway, just to finish up, my dear people, today we looked at hydrostatic pressure, pressure measurement, buoyancy principle, the effect of volume on buoyancy, and I indicated to the mathematical problems that are all in the playlist as well. Yeah, well done. And next week we are going to be looking at dimensional analysis. Remember these letters M, L, and T. Okay, people. Bravo. Bye.